Hello everyone, welcome to part 9 of the video lecture on registers, a sequential circuit, one of the main sequential circuits. So here we will discuss something called universal shift registers. So far we saw many variations of register. So the major categories are like how we are feeding input to the register as well as how we are taking out from the register accordingly. So we can input data serially and we can take data serially, like serial in and serial out. Similarly, serial in and parallel out, right, where data output lines are simultaneously available, and then parallel in, serial out, parallel in and parallel out. So like that four main category we saw, and out of them the other than this parallel out, all others are shift registers, where for taking the data, for inserting data serially as well as for taking the data serially out from the register, we have to do some kind of shifting operation, right? So by default the shifting is towards right. From leftmost flip-flop we will shift information one by one towards right, but at the same time in the last video we saw bidirectional shift registers also, where we can do this shifting both direction, from left to right and right to left, right? These are all the things we saw so far. Now if you can come up with a single register that can do all these things, like if you want to do perform it like CISO register, it should be able to do serial in, parallel out, parallel in, serial out, parallel in, parallel out, shift to right, shift left. If everything is a single register is capable of doing all those things, we can call it as a universal, because it is something which can do everything, right? Universal shift registers. So that is the theoretical concept is I just taken from the textbook and it is written here. So if the flip-flop output of a shift register are accessible, then information entered serially by shifting can be taken out in parallel form, from the output of the flip-flop. If parallel load capabilities, so all those things are explained there. So what are all the requirement of such a universal register? It's something like we need a clear control to clear the registers to 0. So you know that clear and preset, if we are having both at any time, we can clear all the flip-flops as well as we can preset all the flip-flops. So whether it is clear or minimum we need clear. Then a clock input should be there, that is going to synchronize the operation of the flip-flop, and you know how this clock is applied and all, right? So and there is a shift to right control. So sometimes we want to shift the information towards right, sometimes we want to shift information towards right. So accordingly we need a control line that decide what the direction of shifting operation. So the shift to right control to enable the shift right operation. So when you are shifting right, accordingly the serial input should be fed into the register, right? And accordingly we should take the data serially out also. So the serial input and the output lines associated with the shift to right. So whenever we are shifting information towards right, there should be some way from which information should enter the register one by one. So that is the serial input line. Similarly, the point from where the information is leaving the register, so that is a serial output line, right? So that is also needed. Similarly, if you are shifting left, accordingly we need a shift left control, and that will say whether to shift left or not, left or right, right? So it could be a common control line. So that to enable the shift right, shift left operation and corresponding serial input and serial output associated with the shift left operation. And we should have the parallel load control also. We need parallel output lines, because if you want to insert data into the system parallelly, there should be parallel input line, and also there should be a control line saying whether to parallelly insert the data, load the data into the register, or do that shifting operation. That is why we are having a control line, because sometimes we want to insert some new fresh data into the system, or sometimes we want to do the shifting operation, or we want to retain the old information, and that can be controlled by a parallel load control line, right? So using that we can insert the data, and to insert the data some n input lines are also associated with the parallel transfer, right? Similarly, if we need some n parallel output line for taking the data simultaneously. Now a control state that leaves the information in the system unchanged in response to the clock. Sometimes we don't want to do any shifting or loading, nothing, right? We just want to keep the information as before, right? So that also can be decided by a control line which is saying like keep the information as it is, right? So that also we need it. So whatever things, whether we want to keep the information as it is or shift right, shift left, parallel in, parallel out, everything should be capable of done, and we need a single register for that. If something is capable of doing all those things, so if the register has both shift and parallel load capability and all those other things we discussed so far, it is referred to as a universal shift register. And now this is how we can implement a universal shift register. So this is something I taken from NPTEL. Previously what we saw is from your textbook. So this is something a very apt definition I felt, is that is why taken as it is. A universal shift register is a bidirectional shift register. That means it can shift data in both direction, whose input can be either in serial form or in parallel form, and also whose output can either be in serial or in parallel form. So this is a very clear definition that says completely what we are expecting from a universal shift register. We should be able to input data serially or parallelly as per our wish. We should be able to take the output serially as well as parallelly, and also there should be a bidirectional movement, right? So both that also we need. So that about it. Now typically, so it looks like something. So this is a shorthand notation of the so-called universal shift register, and we will see the detailed implementation in the next slide. So here what is this notation? This says that the k bits of information is fed into the system. So this is a parallel load. Okay, so this is your. So if you are writing like this, this means k bits are inserted in the system. So this is nothing but the parallel load, right? Parallel load. And similarly, there should be a parallel output facility, right? And this is these two things, whether you want to shift to right or shift to left. In both the cases, we have to input the serial data, right? And that serial data, it will come from one of the directions. So this is our serial input facility, and that also right or left, like that. Okay. And then the clock is applied, and there is two control lines. So in the previous slide we saw that we need a control line for shifting right or left, for that decision making, whether to parallelly load the data or keep it unchanged, like that. We saw many control signal, but actually for implementing all the functionality that we need, it is enough to keep two control line, S1 and S0. And how it is going to work, it is something like this. See the control input. So these are all your control inputs, right? So this is your control input, and 2 bits are there, right? So we can assume 4 combinations, 0 0 0 1 1 0 and 1 1. So this is how I am assigning different functionality for different combination of the control input. You can design in a different way also. As per this table, you will see how it can be designed in the next slide. So 0 0, say it corresponds to no change. So if at any time, if I am giving S1 is equal to 0 and S0 is equal to 0, that means I do not want to change the data. I want to keep it as it is. Okay. And 0 1, let it be the right shift operation. So that is my requirement. And 1 0, let it be for the left shift operation. And sometimes I want to load the data parallelly 1 1. Now you may be wondering, what about the parallel output facility? This parallel input is parallel load, right? That is by default, right? Because output lines are there. You don't have to. So at any time, this if you want, you can take that parallel output. But parallel load, whenever you are saying, that time only that load should happen. That is why we need a control line for that. Sometimes you don't want to load new information, you want to return the old information, or you want to do some shift operations. That is why we need a separate control line for that. Parallel output, it is not in conflict with anything else. At any time, from the output parallel lines, you can take the output. Similarly, right shift and left shift, that should be decided by the control lines. So that is why we need a different control line combination for that, and no change also, like that. So these are all the main requirement, and this figure illustrates how it can be implemented. Now it's very interesting. The 4 combination we will see. What I can do is, I will keep 4 copies of the same page. 1 2 3 4. I hope. First copy, second copy, third copy, fourth copy. I think more than 4 copy created. Anyway, so this is the first copy. So what I am trying to show you is how it will behave when S1 is equal to 0, right? And S0 is equal to 0. This is a very first combination, right? I am applying S1 and S0 0 0, and you know 0 0 corresponds to no change. Let's see whether it is capable of doing that. So you know, this is our multiplexer, right? So multiplexer, these are all the input lines, and this is the select line of the multiplexer. So all multiplexer select lines I am applying 0 0 as a input. So this is a 3-bit universal shift register. We will be using 3 flip-flop on the background, right? So at any time we should be able to store as well as shift 3 bits. So that is is a meaning. So the inputs of the multiplexer, why I am using, so here I am using a 4 by 1 mux, right? So this is a 4 by 1 mux. So here also I am having a 4, so that is why I am having 2 select line, okay. And for the 4 by 1 mux there will be 4 inputs, a 0, 1, input to 0, input to 1, 2 and input to 3. So here also I am having 0, 1, 2, 3. Here also I am having 0, 1, 2, 3. Now tell me, 0, 0 corresponds to this one. So at any time this bridging will happen as I am fixing this, okay, let me use a different color for bridging. So as I am giving it as 0, 0, what will happen? So this input will be connected to the output. So this bridging will happen. So this will happen at all the 3 mux, and you can see what is being connected to the output, what it is. So this is nothing but this. What is this Q1? Q1 is this particular Q1, right? So I am actually taking that Q1, and here also I am taking this Q2, I am taking, fine, and here also I am taking this Q3. What does it mean? It is simply trying to retain the last information. I mean, what is my Q1? I want to keep as it is. What is my Q2? I want to keep it as it is. I don't want to change the information. That is the meaning. Hope it is clear, right? 0, 0, 0. I mean, for the first combination of the control line, how it is working. Similarly, now let's see. What about the second combination? S1 is equal to 0 and 0, 1, right? So let's see here. So this corresponds to 0, 1. 0, 1, here also 0, 1, and this 0, 1 and the inputs are like this is your input to 0, input to 1, input to 2, input to 3. Here also 0, 1, 2, 3. Here also 0, 1, 2, 3, and you know 0, 1 corresponds to this one. So this will be bridged to the output. So again here this bridging will happen, and here also this bridging will happen. Now tell me, what is this? This is let's observe it. That 0, 1 it was for right shift, right? So that is what is written. And how this, so let me write it here. When I am giving S1 is equal to 0 and S0 is equal to 1, it is performing right shift. Let's see, let's verify it, okay. So what is right shift? The input should be fed into the register from the rightmost end. So this is the rightmost, right shift means shift towards right. So from leftmost end I will fed the input, right? So this is the very first input to the register. So that is the serial input. So the serial input is coming like this, right? The actual serial input is coming like this. Now this should shift, I mean the output of the first flip-flop should be the input to the second flip-flop, then only that right shift will happen, right? Hope you remember that. So output of this particular flip-flop Q1 is actually connected here, right? And this is what is bridged to the input of the second flip-flop, right? Similarly, the output of the second flip-flop is connected here, that is Q2, which is bridged to D3, fine. So it is now performing as the right shift operation, right? Similarly, this is what we saw first, that is when S1 is equal to 0 and S2, not S2, S0 is equal to 0, we saw that it is working, it is retaining the information, right? So this corresponds to no change. Yeah, now the third combination, that is when S1 is equal to 1 and S0 is equal to 0, 1, 0, right? 0, 1, 1, 0, 1, 0 corresponds to this 2, right? This will be enabled. So 1, 0 corresponds, I don't have to show this, right? So and you know the input. So this is the second input. So this will be bridged to the output. This is what is going to happen when you are applying S1 is equal to 1 and S0 is equal to 0. So 1 and 0, 1 and 0, this third one will be bridged. Now on the background, see what is happening. Let's see, what we need is actually this for 1, 0, what we need is shift left operation. So shift left means from the rightmost end we will feed the input, and that should be shifted towards left. So the rightmost end we are feeding the input. See, the input is fed through the I want to shift it towards left. That is why the serial input is coming like this. So the combination is like S1 is equal to 1 and S0 is equal to 0. This corresponds to shift left. And after that, this rightmost flip-flop, its output, right, this Q3 should be connected as input to this one. So that is happening, right? Hope you remember this this feedback kind of connection. Similarly, this Q2 should be connected as input to its previous flip flop. So that is coming like this. So the right, nicely it's working as the as what is expected, the left shift operation. Now finally, this is the last combination when both are 1, right? Both the control lines are 1, and hope you remember it corresponds to the parallel load operation. So let me write it here. S1 is equal to S0 is equal to 1. This corresponds to parallel load. Let's verify that parallel load, whether we are able to load the information parallelly or not. Yes, this kind of a bridging will happen, right? The last input will be connected to the output of the multiplexer. And what is that last input? D1, D2, D3, the 3 parallel inputs which are to be fed in the system. And these 3 bits are nothing but our parallel input. And we are saying to the system register that you load this input, right? And what about the output? The output is always available if you want to take the output parallelly. So we don't need a separate control line. This parallel outputs are always available, right? This Q1, this Q2, and this Q3. These things are always available, and it is not in conflict with any other cases. So that is why this is our parallel output. Fine. So we don't need a separate control line for that. So hope it is clear. It's a very important concept. You can expect this for your university exam, because it is something more powerful, right? It can do everything. Everything is done at a single place, right? Something like that. Thanks for watching. Hope it is clear.